Hello, everyone. For those of you who have not seen me, my name is Miloš. I'm from the Data Science Organizing team, and I'll be hosting a few of these talks right now on the quantum track. First up, we have quantum natural language processing by Professor Bob Coecke, Cambridge Quantum. Can we get Bob on the program?
Okay, hello.
Hi, Bob. How are you?
I'm okay.
My bandwidth is a bit low, so I'm not gonna take up any more of your time. Please start your presentation.
Okay. So I'm going to talk about quantum natural language processing, but I'm going to, in one sense, be a bit more general and talk something which we call compositional intelligence, which is supposed to be an alternative to artificial intelligence. And then we're going to specifically talk about a software package which we make free, open source, which enables anybody to do quantum natural language processing now today on quantum computers. So that's freely available, as I will tell you. So about myself, I was at Oxford University for some 20 years as a full professor. I left about a year ago. At Oxford, I built a big group, about 50 people, and a lot of them left with me to Cambridge Quantum. I'm chief scientist there, and recently we are actually now in the process of merging with a good chunk of Honeywell, and so we'll be by far the biggest quantum company in the world. So I've got my own team in Oxford still, sub-team, and which is dedicated to AI and quantum natural language processing. So we're about 30 people now. And one of our people is Steve Clark, is our head of AI, who previously was at DeepMind. Right. So let's say a little bit about AI today. So there's, of course, amazing progress in NLP and AI, and this is mainly driven to the huge increase in computational power and also a huge increase in available data, but much less due to a shift in a conceptual paradigm, because pretty much the conceptual paradigm today is kind of the same, has been around for more than 100 years. Now, there's a few well-known shortcomings: lack of interpretability, verifiability, safety, fairness, huge cost of data computation in terms of money, time, carbon footprint is becoming pretty bad. And there is, in particular, a lack of combinability with other successful computer science tools and methods. So there's very few things actually blend very well with the learning methods. Now, how does modern CS deal? I'm not saying modern AI now, I'm not modern machine learning, but modern computer science deals with things like lack of interpretability, verifiability. Well, they get increased verifiability and safety and all that from the concept of compositionality. This also allows to combine different tools and methods with each other, and writing modern software without compositionality would simply be impossible. Now, it's a kind of a specific form of compositionality which people use today, which is called Frege compositionality, which goes a long way back, and which says that the meaning of the whole is the meaning of the parts plus a structure. So you need to understand the parts of a system plus a structure, how they plug together to actually understand the whole. An example is basically, to some extent, if you understand the words in a sentence and you understand the grammar, then you understand the meaning of the sentence as a whole. And this is the same is true for all the software, the way it's set up here, how mathematics even works. However, modern machine learning doesn't obey this particular notion of compositionality, and that's why it's not combinable with a lot of the existing computer science methods. In particular, in a lot of machine learning now, the whole determines the parts, so the kind of black box neural network, and that, of course, causes the lack of interpretability. And this also means that a lot of the good old-fashioned AI structures have no place anymore in modern machine learning. Because so what we are going to propose in alternative to all of that, I'll start with our prehistory. So a long time ago, 2008, I mean, in machine learning terms, that's a long time ago. At Oxford, there were 3 people. There was Marusha Drzadeh, now faculty at UCL, and she knew a lot about grammar algebra, the structure of grammar. This goes, I mean, I think most people know more or less about that. It's sort of the Chomskyan stuff, where if you given types of words in a sentence and the way they are plugged together, these are bits of algebra which tell you when your sentence is correctly formed. So you got primitive types like nouns, sentence types, and then things which are not primitive types, so like a verb type, which basically corresponds to the fact that a verb on its own doesn't really mean anything. It needs an object and a subject. So what these little bits of algebra do then is you take this verb type, you plug a subject on the left, an object on the right, they cancel out due to the algebraic structure. I'm not going to go too deep into it. And then you end up with a sentence saying that a subject, transitive verb, and an object together make a valid sentence. Now, what's important for us is not this little calculation, but the fact that you can actually represent this little calculation, this cancelling out of a noun, and this sort of inverse of a noun here, by like these cup-shaped wires. And then the sentence type is just retained and carried through. So this is a little bit of algebra which will help you understand when a sentence is well formed, and that was sort of the thing Marnouche knew. So we're talking 2008, so deep learning and all of that wasn't really there yet. It wasn't really as prominent, and the sort of domination of machine learning wasn't there yet. And people looking at vector space NLP was to some extent still very academical, and Steve Clark was one of the people who did that, and he just moved as faculty to Oxford at the time. And me, myself, I was doing something completely different. I was developing something called Categorical quantum mechanics, which is a purely diagrammatic presentation of quantum mechanics. You can find all of this in this book. This book is now about 4 or 5 years out. And this is a full presentation of quantum mechanics purely in diagrammatic terms. But at the same time, it's very rigorous mathematics. It's not just illustration. This is very rigorous mathematics. And for those who know the term, this is actually all called all-category theory, presented in a very friendly manner. So that's the thing I knew. I started to develop this in 2004. And one thing which is famous, becoming more and more famous in the quantum computing arena, which is part of that, is ZX calculus, which is also from around 2008, which is now being used by lots of the major companies. So generally there is now within quantum computing a new quantum mechanical formalism being used that, thanks to the technological progress being made, actually is proven better than the usual quantum mechanical formalism for many things. In any case, so there is this diagrammatic quantum formalism, which we started to develop in 2004. And let's go back to the people at Oxford. So there was the Marnouche who knew grammar algebra, and Steve who knew vector space NLP. And Steve asked the question, why are there no dictionaries for sentences? Obviously, we know why there are no dictionaries for sentences, because if we know the meaning of words and we know the grammar, then we can typically figure out the meaning of the sentence. That's the Frey compositionality I mentioned. A better way to say it, and actually more general way to say it, is how can we combine grammar and meaning in a meaningful manner? And there was a non-trivial problem. And okay, here is the solution. So in 2004 in Montreal, I was giving a talk about my new quantum mechanical formalism. I was presenting quantum teleportation, which looks in pictures like you see here. And in the audience was a person, Jim Lambic, who since the 50s has been like the biggest name as far as the mathematical presentation go, associated with this grammar algebra and these things. Like, for people know the name Chomsky better, but like the sort of mathematical backbone was mainly developed by Jim Lambic. So he was in the audience, and when he saw me present teleportation, he said, "Bob, this is grammar." He immediately recognized that my diagrams were exactly the same as what he at the time had newly developed as a state-of-the-art of grammar algebra. He says it's exactly the same thing. So going back to the question, how to combine meaning and grammar. So meaning are vectors, which live in a vector space. So obviously they're the subject of quantum mechanics, because quantum mechanics is all about vectors and states. The diagrams which represent quantum mechanics in this formalism, that's exactly grammatical structure. And actually it's richer than grammatical structure. There's much more linguistic structure hiding in there. So the obvious thing to do was to take this categorical quantum formalism and take it as a new theory of grammar, of language, where grammar and meaning are combined in a well-informed manner. And when you if you don't know the math exactly, it may sound mysterious, but if you understand the math, then you know this is very canonical. This is not sort of mystical or hippie or anything like that. It's a very canonical way to combine meaning and grammar to use this quantum mechanical formalism. The sort of way it kind of works is this is a picture which could both represent like a quantum protocol, or that could represent like a linguistic algorithm. As a quantum protocol, you would think of these things as states, Alice, H, and Bob. They're just states of quantum systems. And you would think of these things as operations. For example, what's called the Bell measurement, a post-selected Bell measurement. So this could be interpreted as a quantum protocol. Now, this also can be interpreted as an algorithm that computes the meaning of a sentence from the meanings of the words. So what we have now is these are not quantum states anymore. These are now meanings of words, like vector embeddings, like people are now using all over the place. And then what this is just a linear map you apply to these vectors, but which represents the grammatical structure and which guarantees that the meanings of these words interact in a way that they actually produce something which is representative for the meaning of the sentence as a whole. Of course, we did a lot of experiments with that with real world data, and it all worked out very nicely. So it all made perfect sense. So you can do things then, like, for example, compare by taking this is an inner product I'm taking here. By taking other inner product, you can compare the meaning of, say, Alice hates Bob to Alice does not like Bob, and so you can use you can start doing the stuff which people used to do with words now with entire sentences. This got a lot of attention, but we at the time we never thought of it as having anything to do with quantum, really. We even tried to avoid any quantum connotation because we thought we were going to be branded crackpots. But of course, the media didn't listen to us, and they started to brand us as quantum linguists and stuff like that. And then we went to hide somewhere under a table because we thought that everybody would think we were crackpots. Okay, that was then. That's more than 10 years ago. Now, so here is a little table, and you can compare the power of that formalism that we had then with, say, NLP and AI now. And the formalism is better at a number of things than what that AI did. I come here, I've got a big list here. For example, the compositionality makes it interpretable as opposed to the black box of most of AI. On the other hand, this doesn't have the sort of universal properties which machine learning has in terms of curve fitting, so it doesn't have that. So there were some pros and cons on both sides. Well, I mean, that was that. So I'm now comparing what we had then to how NLP and AI is now, right? But we haven't sit still, of course. Like this was our old work, this was our prehistory, like I say, and we're now working with something new, which is further development of the same thing, which we call language circuits. So this I propose this in a paper which came out in 2019. So it is quite recent. And one way to say what this is before, and all these grammatical gadgets, they were always restricted to sentences. What is the structure of a well-formed sentence? That's typically what it was about. So we lifted that to actually entire text. It wasn't just an extension. Things had to change to some extent. And one of the things which changes, which we think is a big plus, is that while in many vector embeddings and all that, meanings are static. For example, like GPT-3 doesn't know that there was a COVID epidemic because it was trained before. The sort of formalism here we're dealing with for language is all about updating all the time. You're updating your meanings all the time. So it's not about static meanings, it's about evolving meanings. And it makes a lot of sense when you think in terms of text, because if a text progresses, you learn more about the actors or the agents into it. And then obviously you update your meaning about the characters in the text. So it makes a lot of sense to do that. So that's this. What we did formally to achieve that is we borrowed some more stuff from categorical quantum mechanics. And one of the things which we use in categorical quantum mechanics is what we call spiders. And they're sort of diagrammatic dots, like here, they're nodes. Well, think of it as neurons if you want to. But they have this very beautiful property that if you glue two of them together, they fuse together. Of course, they wouldn't be very useful in this form as neurons because obviously they're a bit stupid if that's their behavior. But on the other hand, they're very powerful as a tool to represent connectedness and other sort of interactions between richer structures. So algebraically, they're fully characterized by this behavior of fusing. And what we can do is basically, we've got a sentence, Alice hates Bob, like we had before, and then we give some sort of internal structure to this verb, to this transitive verbs hates, using these two spiders. One can prove that it is fully justified, both formally and empirically. You pull this out, and you get something that looks more like a circuit now. And you see, once you got a circuit, like you got the Alice wire, you got the Bob wire, the beer wire, I can start I can compose a sentence, Alice hates Bob now with Bob likes beer, and then I could go with Alice like dropped Bob's beer or something like that. And I can go on, I can start building text with the same sort of diagrams I had before. So that's this idea of language circuits. They have a lot of advantages like the evolving meanings. And a very interesting thing, which we only start to understand recently, is that going to these circuits, like what I did, they actually strip away language-dependent features of grammar. What do I mean by that? I gave the example earlier of a subject, transitive verb, and an object. Of course, this order is very specific to English and some other languages. But in fact, for every possible permutation of these three, subject, verb, and object, there is some language in the world where that order is done. And so there's a lot of language-dependent bureaucracy, I would say, language-dependent bureaucracy in language, which makes actually specifying grammatical structure and linguistic structure in general really difficult and really complicated. And that's why it's not being done at the moment in NLP. It's just all being learned because it's quite complicated. However, if you strip away all this language-dependent stuff and other stylistic stuff, which is happening in the circuits, for example, this I can say this in two sentences. Alice ate Bob and Bob likes beer, but I can also say Alice ate Bob while Bob likes beer, for example. So there are different ways to bring these things together, either as two sentences, one sentence. So you got a lot of stylistic choices to turn this into actual language circuits. And then you also have the choice in which language you're going to turn it, because they don't really depend on language anymore. And so this makes actually the whole thing much more economical. So we sort of crafted our own grammatical gadget, which to basically capture language in general. And this is how like a language with a sentence with the bureaucracy would look like, while the circuit would be something much simpler. The language independent circuit, and it's generative, so you can actually you can generate language in this way. It's interpretable because it's all much more transparent now. It's verifiable, stable, fair, all the things you want. And I started this discussion with the traditional notion of compositionality, which is bottom up. So we came up with a new notion of compositionality, which is compatible both with quantum theory and with modern machine learning, and which still gives you all what you need from compositionality, which is the insights to actually know what you're dealing with, actually, the sort of interpretability. So we've done all that work. You would expect it to be cheaper just because of, of course, this is a statement which is hard to make if it's going to be implemented on, say, on a quantum computer or something like that, which we're going to go next. But anyway, we expect this to be cheaper in the longer term. And one of the nice things is this categorical quantum mechanics is a reasoning system. So basically, we're combining empirical methods with actual logical reasoning, which is something which seems to fail to a great extent for other people who are trying this in different ways. Anyway, you just find everything in here. These are three former students of me. So they basically prove that with this diagrammatic formalism, this logical formalism, you can actually prove everything about quantum theory. Every equation you can prove using linear algebra. So it's a what's called a complete logical system with respect to empirical data, if you want to. So this is the first of its kind. A logical system that is complete with respect to empirical data modeled in vector spaces and things like that. So, can't go in detail, but with this new formalism, we in principle beat NLP and AI as we see it on all fronts. We can think, oh, wow, that sounds great. But there is a problem. There's a problem. I'm going to skip this. The problem is that this stuff is exponentially expensive on a classical machine, which is a big problem, of course. It's a huge problem. These structures, these linguistic structures, they're just, you end up with a tensor network, which is very expensive to implement on a classical computer. But okay, let's write on a quantum computer. Because they're coming. So the first proposal for implementation of this sort of stuff, which was still the first generation of theory I was talking about, was done by Will Zhang, then a PhD student of mine and myself. Will is now the head of quantum at Goldman Sachs. He's now the head of quantum at Goldman Sachs. And so yes, we basically, that is the obvious thing that I say, these things are exponentially large. So on a quantum computer, this exponential size just vanishes. There's no problem anymore, because that's the whole reason why quantum computers started to be considered initially. And then we also showed that you could come up with a lot of speed-up algorithms, a lot of standard quantum algorithms automatically translate in a very natural way to standard NLP tasks. So this is an example of an algorithm. I'm not going to go into that. So that's nice. Like now we've got some quantum speed up also for our. This is still our old formalism. Now it's one thing to write a theory paper, and then another thing is actually to implement it on an existing quantum computer. So we start seriously consider this in about a little bit over a year ago, and of course we had to adjust to the sort of quantum computers which are available, and in particular the way you can encode data on these machines is non-trivial. You can't just say, okay, here I've got some classical data, I'm sticking it on the machine. In fact, you need to use some machine learning to actually get your data on the machine. Basically, what you do is you train your quantum computer, you take some circuit, there's a lot of variables, and you train the machine with data, and that's actually how you get your data on your machine. This is very much like training a neural network. That's what pretty much everybody who's working with quantum computing is doing now. They basically train the circuits and all that. So we developed a theory to do that for the specific case of language. Basically, to illustrate this diagrammatically, so we have a circuit here, and then you use this ZX calculus to deform the diagram a bit more, and then you end up with what is quantum circuit, which is parameterized. So it's this parameterized circuits which we will be training. Right. So okay, this is diagram. So basically, you've got these variables in your circuits which we train. You use a classical optimizer, and that's sort of the methodology you do. So we did it. We did it first on IBM hardware. This is now more than a year ago. Fairly small scale. More recently, we did it bigger. We are now starting to work with corpora of multiple hundred sentences, and we are now moving towards 1,000. So it's surprising that you can even do anything like that. It's really surprising that you can even do anything like that. And the only way it's possible is because we're not doing the brute force learning stuff. We actually bring in some structure, which is this linguistic structure I was talking about in terms of these diagrams. And that's what makes it even possible to do NLP on a quantum computer, given that quantum computers are fairly small at the moment. I mean, they're small in so some of them are like, there's IBM now has one of more than 100 qubits, but it's not obvious to use all of them in like a useful manner. So when I say size, it's not just about number of qubits, it's about the noise levels and things, and the time it takes to do multiple training steps and things like that. And so there's a lot of things which come in there, but we are doing pretty well. So basically, we developed software to do all these things, and this is now all freely available. So Ford made a big fuss about it, that we actually now made open source under the name Lambeck, all the stuff which we use to do this quantum natural language processing. So we invite everybody to do that. We also have a Discord server where we help people doing all these things. If you write us, then we can point you in a direction. So basically, what the software does, which is available, is you put text into it, language text, and then it spits out quantum circuits, which then through our compiler, which is also available in open source, Ticket, can be directly fitted on any quantum hardware. You can pick whatever hardware you want, and you can stick it there. Right now, what's particularly nice about this circuit view of natural language is that so there's a lot of quantum machine learning being done these days. People are doing quantum machine learning. We are in a very different category, in fact, in what we are doing, in the sense that the real origin of quantum computing, or the real boom, or the real whatever, started really with Feynman saying simply that if you've got a quantum mechanical system and you try to simulate it, you better use a quantum mechanical computer, because otherwise it's going to be exponentially expensive. We're pretty much in exactly the same situation with our language model, because it's quantum model, it's exponentially expensive on a classical computer. So you get the same exponential game on a quantum computer, and we are now looking at algorithms which are direct translations from what people use in quantum chemistry, where the biggest promise is to be considered for quantum computing. But we use exactly the same algorithms, but now in the case of quantum natural language processing. So we are much more in the category of like simulating quantum systems with a quantum computer rather than doing something like quantum machine learning. Although a lot of things, some aspects like the getting the data on the machine are borrowed from quantum machine learning. So okay, so we got now also in terms of quantum speed up a really nice bonus, which is better than all the rest. So yeah, so I'm not going to say too much anymore, but basically all what I've been saying is not restricted to language alone. We are building models, models of cognition and things like that, which go way beyond language alone. For example, we bring in Karen Force conceptual spaces. We have compositional theories of physical space, movement in physical space, perception of physical space, which we all put under the same umbrella now. Like, I mean, this is, for example, these diagrams can be used to specify chess positions and chess moves and things like that, which is all possible. So this is about a complicated physical space, in fact, and you can combine all of them, and then you get basically a new model of AI, a new model of intelligence, and which will all be quantum native. It's stuff which really needs to be on a quantum. We're trying to put it on a classical computer too. We're trying it, but it really wants to be on a quantum computer. I mean, people have been working with chemistry on classical computer for ages, of course, but it's not the natural thing to do. So now, as for something completely different, we basically, just to have a bit of PR, we basically start to generate music using an NLP, because you can use grammars for music too. And then yesterday, a miracle happened. One of our quantum computing generated songs ended up on #1 in the classical charts. So this was a song produced by our quantum NLP machinery, and yeah, you see, we're even above an Adele cover or something like that. Anyway, so just an example that all this machinery is very broad, this compositional machinery, and we're only starting to develop it now. My team is now 30 people. Like a year ago, we were basically 4 part-time, so it's growing a lot, and the quantum computers are growing a lot too at the same time. So thank you. That's where I'm going to end.
Hi, Bob. Thank you for this wonderful presentation. Regarding questions, well, you have mentioned that you've been trying for the past year to implement all this natural language processing on quantum computers. What is there like a timeline that you can give us on when you expect this to really take off?
I mean, a lot of it depends on the progress in the hardware, of course, which is not in our hands. It's kind of becoming, to some extent, in our hands with this merger with Honeywell. So we're going to have in-house hardware. I mean, so what we want to do next is showing that there is something meaningful we can do on a quantum computer, which would be impossible on a classical. That would be our first step. And I think the hardware is almost there to do that. The hardware is essentially there. So this is something I expect that we can do within the year, definitely within 2 years. Definitely within 2 years. Now, from meaningful to practical and commercial, that's still
a long way,
another step. If some of the promises made by the hardware companies are true, then this would be 4 to 5 years. But that's not something we can guarantee. That's not something we can guarantee.
Of course. Yeah, yours is to find a practical use for it, and then maybe bring some attention because of it, and then we let technology take its course, and then maybe in the time frame we get.
It's a very interesting landscape, the hardware development, because they're completely different systems. There's like the IBM system, which is very different from, say, the Honeywell system, and then now a bunch of people are starting to build quantum computers with optics. If they can pull it off, this is going to be a huge deal, because light doesn't need to be cold.
So much faster.
It's very stable and all that. So if they can pull it off, so they have a problem. I know somebody, and they think 5 years that they can come up with 1 million optical qubits.
Yeah, well, there are optimists, there are pessimists. And always regarding these kind of new and interesting technologies, you really can't have an accurate
You
answer
can't tell. On the
when
other
it's going
hand,
to take off.
so, so, so some of these things have typically take much longer than expected. I should say that the recent progress in quantum computing has been much faster than expected by the majority of people. The way it's been evolving the last 2 years, it's almost a self-fulfilling
Yeah,
prophecy to some extent.
yeah. Okay. That's all the time we have and questions. So, Bob, thank you very much.
Thank you. Bye.
See ya.
Bye.